All year long, we're concerned with electron structures. Electrons determine bonding and chemical reactions. So you're going to see these electron configurations all year long. Let's do the calcium atom. Calcium atom. Number 18. The atom would be 1s2, 2s2, 2p6. Then next is the 3s for 2, the 3p for 6, and finally 4s2. Here's my electron configuration for the calcium atom. The valence electrons are the electrons in the outermost energy level. Right now, the highest energy level is the 4, the 4s with 2. These are my 2 valence electrons. We would like 8. So we have 2 options. We could just lose those 2, because then if we did, the next highest energy level is the 3rd, and the 3rd is filled with 8. 3s2, 3p6. So we could either lose 2, or we could gain 6. But we'd have to find other atoms or ions that are willing to give us 6 electrons. So in the long run, you're probably thinking the same as I am. Lose 2, right? Let's just lose these guys. When you do electron configurations for ions, you have to take the charge into consideration. So that calcium atom is just normal calcium neutral. The calcium ion is charged +2. Calcium is going to lose those 2 outer electrons, but we're not losing protons. So if I still have 20 protons, but I've lost 2 electrons, I only have 18 electrons. Overall, my charge is +2. So when you do the ion, you have to take the charge into consideration. +2 means lose 2. So the calcium ion is just 1s2, 2s2, 2p6. And then here come my valence electrons. The 3s2, 3p6. Here are my 8 valence electrons. Valence electrons in the calcium ion. And again, we said 18 electrons. That's normally argon. Well, yeah, now calcium has an electron structure that looks like argon, which is stable because all the orbitals are full. We have 8 valence electrons. The charge then on the calcium ion, we mentioned, is +2. Calcium +2. If we take inventory, we still have calcium element number 20. So there are 20 positive protons, but now we've lost 2 electrons. So we only have 18 negative electrons. Overall then, our charge is +2. There's a question somewhere along the line that says calcium has a +2 charge because he gains 2 protons. Wrong. When we form ions, we are not changing the nucleus. That would be a nuclear reaction, and we don't want that. We can't do nuclear reactions in the lab. We can do chemical reactions, which involve changes in electron structure. So the way that you get a positive charge is not by gaining protons. It's by losing electrons. We still have the same number of protons. But if we're down in the electron count, we'll have extra positive charges. We could also do this with a negative ion. Look at nitrogen. Okay, so the nitrogen atom. Nitrogen is element number 7. 1s2, 2s2, 2p, 1, 2, 3, 2p3. My valence electrons are these guys right here. There are 5 valence electrons. All the electrons in the highest energy level, which is the second. 2 in the S, 3 in the P. Okay, so we want 8. So we ask ourselves, lose 5 or just gain 3? What's easier? Whatever involves less electrons. The less shuffling of electrons, the more likely it is to occur. So let's gain 3. So as an ion then, the ion, if I gain 3 electrons, I'll be 1s2, 2s2, 2p6. So then here are my valence electrons, and now I have 8. 8 valence electrons. We filled that last p orbital. Now to determine the charge, let's take inventory. We have 7 protons. 7 positive protons. It's element 7 nitrogen. But now I have 10 negative electrons because I gained 3. So my balance and charge, -3. Ah, cool. So the ion would look like this. Nitrogen -3. The way we have a negative charge is by gaining electrons. Perfect. So you can do electron configurations for atoms and ions. So be very careful. There's one of these on the final exam, and people get it wrong a lot, and I always feel bad. It'll say, what's the electron configuration for an ion? You must take the charge into consideration. Of course, the atom is one of the choices on a multiple choice question, and that's usually the one that people pick if they get it wrong. So they picked the right configuration for the atom, they just missed that it asks for the electron configuration of the ion. So that should take into consideration what we need to do, gain or lose electrons, to fill the outer orbital with 8. Okay, so now a couple things that we should mention. Some general vocab. Cation is just any positive ion anion is any negative ion. They're very general terms. So for example, earlier we were looking at sodium chloride, NaCl. The sodium was +1, the chlorine was -1. We would say that the sodium is the cation and the chlorine is the anion. A very general term for anything positive, anything negative. So there could be a question that would say, like, what is the anion in this compound? We want to know what's the negative ion. Or they might say, what is the charge on the cation? What is the charge on the positive ion? Here's how I remember them. It's a little bit of a stretch, but it works. Cation. Kitties. Who doesn't love a kitty, right? Kitty. What kind of funky eyes. Here's my positive bugged out eye kitty. But I always remember it. The negative one's a little bit of a stretch. I think of an ant. I think they have like, what, 6 legs? So here's my anion. It's a happy bug. There. Long negative body. That's how I remember them. The cation is positive. The anion is negative. The last 2 little vocab words, ionic bonds then. Here's the beauty of an ionic bond. They form from the transfer of electrons. Think about sodium chloride. The sodium ion had 1 valence electron. He wanted to lose it. Well, it's got to go somewhere. Somebody's got to pick it up. Chlorine had 7 valence electrons. He wants 1 more for 8. It's a match made in heaven. The moment the electron is transferred from sodium to chlorine, here's our electron transfer. The bond forms, the magical ionic bond. Sodium and chlorine are like best friends for life. And actually all of the alkali metals love bonding with the halogens. The alkali metals all have 1 valence electron, they want to lose it. The halogens all have 7 valence, they want 1 more. Match made in heaven. As the electron is transferred, a bond forms. Both ions are now more stable. It's perfect. Salt is just a name for any ionic compound. Any ionic compound. A very general term. So in the lab, we're going to test some ionic salts. They don't all have to be sodium chloride. I mean, we call that table salt. But salt in general just means anything ionic. So you might hear that term in the lab a little bit. And then finally, to summarize the trend in charge, this is important. In order to predict bonding, eventually we need to know the charge on every element on the periodic table. Whoa. Actually, it's not so bad. We already know that there's a trend with valence electrons. Everybody in group 1, the alkali metals, they all have 1 valence electron. Group 2, they all have 2 valence electrons. We skipped the transition metals because the number of valence electrons can change when you're dealing with those d orbitals. We'll skip them, we'll come back to them later. But the trend picks up again with the boron family. 3 valence, 4, 5, 6, 7, and for the most part 8 valence with the noble gases. I get like helium only has 2. Well, here's the trend with charge then. If all of the group 1 alkali metals have 1 valence electron, they'll all lose 1. They'll all have a charge of +1. If their choice is lose 1 or gain 7, they'll all just lose that 1 rather than gain 7. All the alkaline earth metals have 2 valence electrons. They could either just lose 2 or gain 6. Lose 2. They'll all be +2. We still skip the transition metals. If the number of valence electrons can change, their charge can change. We'll deal with it later. But then when we pick up with the boron family, we have 5 valence electrons, we want 8. Oh, whoopsie, 3 valence electrons. We want 8. So yeah, it's probably still easier to lose 3 than gain 5. +3. But the carbon is the turning point. The carbon family has 4, they want 8. Gain 4, lose 4, what do you think? It can go either way. So we'll put plus or minus 4. And I'll show you some examples where they could go either way. It just depends on what they're bonding with. But then again, that's where it turns. So this is like the boron family, carbon family. Next would come nitrogen family. If they already have 5 valence electrons, it's probably easier to gain 3. They're all -3. Everybody in the oxygen family already has 6 valence electrons. They want 8. Probably best to gain 2 rather than lose 6. All the halogens, fluorine, chlorine, bromine, they will all go -1. They already have 7. They just need one more for 8. And the noble gases, no charge. They don't form bonds. They don't need to. They already have full outer shells. If this makes sense, this trend with valence electrons, and then how we can predict the trend with charge, you are in a very good place for the rest of this chapter.